Hello, everyone. Welcome to the online public colloquium of Kadir Has University. This is our 43rd edition. Today, our guest speaker is Assistant Professor Fabio Stroppa from the Department of Computer Engineering at Kadir Has University. And the title of his talk today is Human-Machine Interaction with Soft-Growing Robots. Thank you so much for joining us. Now I pass the mic to Professor Berker to introduce our speaker.
Well, I'm glad to be here, and thank you very much, Ishim, and thank you very much to all of you, and to, of course, our speaker, Dr. Fabio Stroppa. I should start again by thanking all of you who make this possible by your attendance, by the Ishim organization, but especially our president by her support from the very beginning of the series, which is, I think, a unique series. Every week, we are very fortunate to have excellent, outstanding speakers. Today, we're especially fortunate to have my friend Fabio Stroppa from my own faculty of Engineering and Natural Sciences to talk to us about human-machine interactions. So let me first tell you about Fabio, who joined us recently. We're very happy that he did. He got his BS and MS in computer engineering at the Polytechnic University of Bari, his PhD in perceptual robotics in Scuola Superiore di Santa Anna in Pisa. And then he did a postdoc at Stanford. And then we're very happy that in 2021, from Stanford, he joined us for active research and teaching at Kadir Has University. He will be speaking to us about human-machine interactions, which we all interact, but they're more sophisticated machines, more dangerous, more helpful machines, but I'm not going to steal the lines, whatever. I will let him tell you about all of this. Fabio, thank you very much for being here in general and for being here specifically right now.
Thank you so much for having me and for joining me today. It was a very good presentation, introduction, actually. Thank you so much. Can I go ahead and share my screen?
Please do.
All right. Okay. I think you should all see my screen right now. Okay, so I guess we can start. I'm Fabio, as I already introduced myself. So I'm an assistant professor here at Kadir Has University. And as you can see from the title of my presentation, my research interests are mainly related to human-machine interaction and also artificial intelligence, which is part of all the robotics scientific research. So today I'm going to talk to you about some applications of human-machine interaction and AI in a subcategory of robotics that is recently emerging, which is soft robotics. So I had a slide, no, wait, I lost it. Yeah, this was like a presentation about myself and everything disappeared because technical problems, but we already have an amazing introduction of myself from Nihat. So I don't need to say, I don't need to say most of the things that you already repeated. So I'm just gonna say that I'm a computer engineer, I'm a software engineer, and I did my PhD in robotics. So, and for the last 2.5 years, I worked at Stanford, and today I will just basically tell you my adventure at Stanford. But let's start with a little introduction on the whole concept of human-machine interaction and robots. So as you might know, robots are becoming more autonomous every day. If you have a certain task, then probably there is already a robot that can do that autonomously, whatever that is. Yet sometimes we still want to keep the human in the loop. So the human interacting with the robot. We need the human to be there, part of the overall process. And whether that is to assist the robot in performing the task to achieve better performances, or the other way around, such that the robot can assist the human as well. And that is why we talk about human-machine interaction. So robots and humans can interact in different fashions, as you can see from these videos. And the benefits can range from having robots doing chores for us, solving problems, improving search and rescue tasks, or even helping people with disabilities, Like, I don't know if you can see my mouse in this video here, which, by the way, that's the system I worked with during my PhD. But today I'm not going to talk about rehabilitation robotics, sorry. But I'm going to talk about interaction with, as I already said, soft robots. So soft robots are a very different type of robot, very different from the industrial robot machines that we are used to see every day in movies or in industrial systems. I'm talking about a robot that can grow, that can modify its shapes based on the environment and reach, let's say, targets in a complex scenario. So how do we make this interaction possible between the human and this robot, and how much smart this robot can be? And also, how do we actually design one of these robots to be perfectly capable to solve a specific task? So these are the questions that I will address today while I will talk about my research to all of you. So first of all, some of you might not know what a soft robot is. Well, it's soft. It's made either of plastic or fabric, which makes it very affordable and easy to build. And it can be of many shapes, as you can see from here, from my videos. But the main feature, this main feature is the ability of performing eversion. Eversion is these robots can grow and retract. So basically they can change their length to explore cluttered environments and perform certain tasks. And of course, being soft, they are also pretty safe for humans. And we're talking about human-machine interaction. So this is a very important feature. So before to move on, I actually wanted to show you some videos in full screen such that you can have a better idea of the capabilities of these weird devices. And this is a close-up of how the robots evert, so grow and retract. And also, as you might have noticed from the title of this slide, we also call this particular type of robot vine robot because with its resemblance with plants. And actually, the idea behind these robots come from how plants grow in nature. And I already mentioned cluttered environments. In this video, you can see a robot that is not actuated, which means that when it moves, it is not commanded by motors or by some sort of control. It's just growing and crashes on obstacles and then changes its shape based exactly on the environment. And that's how this robot can explore this labyrinth or maze. Or they can also be used in search and rescue scenarios like this one where the robot is turning off a valve, perhaps to switch off a faucet during a fire. So today I will tell you about my work at Stanford University, in which I worked in Charm Lab with Professor Alison Nakamura. You might have probably heard her name if you are interested in robotics or haptics. And most of the projects over there in Charm, they involve soft robots. And my role as a software engineer were mostly on developing innovative interaction methods and algorithms based on artificial intelligence. So today, yeah, I will basically narrate my adventure over there in California, which was very, very, very an amazing experience, I have to say. So all the things I'm going to say today, they are like in order the evolution of each other. In which different methods are used to make the communication between human and robot possible. And as you will see, I gave the robot different degrees of intelligence, but I also provided humans with easy tools to interface with these weird devices. So the first two parts, these two, if you can see my mouse, those two topics are very related to human-machine interaction, and in particular on how humans can teleoperate soft robots. So teleoperation actually means a remote control. Imagine when you play video games and you're exploring virtual worlds with your avatar. Well, then you are teleoperating that virtual avatar and you're exploring a virtual world. But in this case, you are like commanding a real device. In the last part of the talk, this one, design optimization, I would like to show you some of my ongoing research, which involves application of artificial intelligence technique to build specialized robots for a certain task. It's not really related to human-machine interaction, but it's still related to artificial intelligence. So let's jump into the first part. Designing control for this eversion, it's very challenging. And I repeat, eversion is the robot's capability of growing and retracting. And it is challenging because mathematical models for soft robots are not yet well defined. So as you can see from these videos, soft robotic systems usually rely on humans to operate. However, the differences between the way our body moves and the way the robot moves make it really difficult to find appropriate control interfaces. For example, you can see my colleague here operating the robot with a joystick. So the way I proposed to solve this control problem was to create an interface that allows humans to control the robot simply by using their arm. So let's say that the gestures of the operator would be tracked by a motion capture system, just like in the movies when they do CGI. So they record the animation, they made the animation by recording the movements of actors. So in this case, the operator, the human operator is the actor. And all these gestures are mapped to the robot for, let's say, what it would be an easy and intuitive teleoperation. I call this interface the body interface because it's based on, the body of a person. And I use this interface to teleoperate a soft robot while performing a reaching and grasping task, which means aim for a certain target, collect it, and possibly reposition it somewhere else. This is a picture of the first robot I worked with. It was a prototype, and it was specifically built for manipulation tasks. So it can grow and it can retract. It can also steer in 3D. I know this is hard to see from a picture, but I also have a video that I will show you later on. And it can do all these actions while carrying a payload. In this case, it's just a little cube, but imagine that we could also hold something heavier than that. And this big box on the top is where the robot body is contained when it's not grown at all. So imagine it's revolved around, inside this container. And imagine that the robot comes out from the container and grows in favor of gravity to reach targets from the top in this particular scenario, kind of like an arcade claw machine that you see at a fair. So that was like the idea that we had. And there's a picture of me, that's actually me, wearing the body interface and commanding the robot. But of course, in this picture, I was very, very close to the robot. In a real case, the operator would be further away or even in another room or place because it's a remote teleoperation. You don't need to be there. So how do I control the robot with a body interface? So I want it to be very simple and intuitive. So if you put your arm down, the robot goes down. And if you bring it back up, then the robot retracts. Very intuitive. And the same goes for steering. The robot simply mirrors the gesture of the operator such that you would act as the robot was your own arm, more or less. So all of this seems cool and futuristic, but I know what you're wondering. Does this work? Well, I was wondering that myself. So as a researcher, I ran a little experiment to test whether this works or not. And I asked, I think it was like 12 participants to come to the lab and teleoperate the soft robot while picking up a block and moving it onto a target. And this was before pandemic. So I had a lot of people coming over and playing with this robot and good times. So yeah, this is a small sketch of the setting. And of course I have a picture, but enough talking, let's just watch a video, which is much, much better. So this is me running the experiment, and there is a participant, the guy with a red t-shirt, that is currently teleoperating the robot. And I would like you to look how the robot responds promptly to the movements of the operator, more or less. Let's watch it again. Of course, there is a delay because it's a prototype, it's a research prototype, but it was working pretty good. And then he drops it. There you go. Okay, so without going too much into the details, because I know that if I showed you plots and charts, maybe I would just lose you all. That's not what I want to do. So I will just briefly draw some conclusions about this unconventional teleoperation device. And it turns out that the performance of this interface were remarkable. We achieved 97% of accuracy while repositioning a target. And most importantly, people were really excited to be using their arm to control a robot. So what's next? What's after this? Well, at this point, my objective was to make the robot somewhat smart, such that the synergy between human control and autonomous control would help to achieve better performances. Imagine the robot can do partially the task by itself, and also the human is still in the loop. We want the human in the loop. That's very important. Otherwise, we wouldn't be talking about human-machine interaction. But before to talk about that, if you want to know more about this body interface and also the robot, this work has been published through ICRA 2020, in which I also received a nomination for Best Paper Award in human-robot interaction. And so you can also rewatch a better version of this very presentation on YouTube, where I go more deep into the details and also the results. All right, so let's make the robot smart enough to be part of the decision-making. And in the next step, the control will not be completely relied on the human operator, like we have seen in the previous example. When I say control, I actually mean who is in control of the whole task. And when the human is still operating the robot, then the human is in control. If the robot is a little bit smarter, then also the robot can be in control. So the control will be shared between human and robot, and that's why we talk about shared control teleoperation. So this term, shared control, really is another way to say human-machine interaction. There is not one unique definition or interpretation, and as you can see from this slide, there are a lot of synonyms. However, the definition that I personally like the most from the literature is partial replacement of a function that is carried out by the robot, which allows humans to solve problems that are very difficult to automate. So that's why we have robots and humans together. And a very immediate example of this shared control, even without robots, is a CAPTCHA solver. This is a CAPTCHA. Sorry, I went too far. This is the CAPTCHA, right? So CAPTCHAs are systems made with the only purpose of being impossible to be solved automatically. Like you're on a website and then you fill the form and then the website asks you to prove that you're not a robot. So that's what CAPTCHAs are for. And that is why CAPTCHA solvers are usually services where a real human being is on the other side and solves the CAPTCHA in real time. So there is like this shared control between a software, which is a machine, and a human, which is actually solving the problem together with the software. And the software then is delivering the service. So this is like the idea of shared control or shared autonomy, if you like it more. But let's go back to the case of the robot. And in particular, my study, what I wanted to do is, okay, let's solve a problem, one problem with a soft robot. And let's say, once again, it's a pick and place task, just to keep it simple, very, very simple, not even with the pillars like I showed you before, because this is kind of actually a trick of engineering. So let's keep it simple and then let's complicate it later on when things work. So as you can see from the photo, the robot that I used here is actually the same as before, but now I wanted to make it smart. What does that mean? Well, suppose that the robot knows where the targets are and where the items are, so it can know what to do because, for example, there are cameras and the cameras can track the objects in real time and can send the information to the robot. So that's some sort of, let's say that's the eyes of the robot, right? And then let's also suppose that the robot is so smart that it can actually tell you where to go, or even better, suggest you where to go. So how can we do that? How can we make this communication? How can we make this human-machine interaction? Well, we can make the robot talk through some speakers, for example, but that might be confusing. So imagine the robot tells you to go left and then you think, okay, it's my left or your left. Well, that kind of depends on where you're looking at, where you're standing. Yeah, that's confusing. Let's discard that option. What else? We can use some sort of visual feedback. Yeah, we can have lasers or holograms to aid you with augmented reality that can point you in the right direction, or like those Google lenses that can render things so you can see virtual and augmented reality as you move. But then again, that would be just an arrow pointing in a direction that you actually make out yourself. So it's not too much of a help. So what else what else can we do? Well, what about we feel where to go? What about we felt, like with touch? What about the teleoperation interface that we are using to command the robot would generate some sort of forces pushing you towards the right direction? Yeah, that would be more efficient. So this is called haptics, which means anything related to the sense of touch. So imagine your phone vibrating while ringing or texting. Actually, texting is better because it would simulate a keyboard. Or for example, your video game pad notifying you that you have been hit by an opponent, or a robotic device moving your limbs, like in sci-fi movies. I don't know if you watched Avatar or Alien, some sort of body extender. So in this case, in this very case, imagine that you are teleoperating the robot and the robot pushes you through the interface that you're using to teleoperate, pushes your arm in the right direction, because the robot, again, knows where to go. Unfortunately, the body interface that I showed you earlier did not have any haptic feedback, and rather than trying to add more sensors to the interface, which I tried, by the way, in the end, I decided not to use the body interface because it was too complicated. But instead, I used a classic teleoperation device, such as this one that I have in the picture, which is called Phantom Omni, which is capable of generating this haptic feedback. It is a haptic device. So literally it can generate forces that push you in a certain direction. So we can use those forces as a sort of guidance during the task. And I also have another type of gripper, which looks like a bubble gum. And of course, it doesn't work with magic, but it works with magnets. So there are magnets in the little cube and also inside the gripper. And as the gripper inflates, then the distance between the two magnets would be enough to not generate an attraction force that would keep the objects together. So we decided to use haptics. We decided to make the robot smart. And concerning the way of how the humans can interact with the robot, let's call them interaction paradigms. So how can we how many ways there are to implement shared control? Interaction paradigms. This is what I did. How many ways are there? Well, it's kind of really up to one's fantasy. There are really, you can implement many cases. So I had to narrow it down to a number, to a finite number, and I chose these 6. So first of all, I had the full teleoperation, so normal teleoperation where the human controls everything, so tells the robot where to go, and the robot is not smart. Of course, this is not sheer control, but I use this as a baseline for benchmark comparison with the other paradigms. And then there are these 2 with haptic feedback, the haptic feedback that I just discussed to you, in which the robot pushes you towards the right direction. One paradigm, this fixed assistance, only have assistance there, meaning that the robot never leaves you alone, always tells you where to go. And the other one, which I think is more interesting, is with the so-called assistance needed paradigm, which comes from rehabilitation, in which the robot produces these forces only when you kind of need them. So let's say that the robot also understands that you're not doing that well. Maybe you're going in the wrong direction. And as soon as it understands that you're doing it wrong, it kind of pokes you a little bit and pushes you, saying, okay, this is the right way you should do the task. And then when you start doing it right, the robot stops helping you. And then without haptics, going more towards automation, there are these 2 paradigms that are actually specifically built for soft robots. So what I did is to split the robot directions of movement, which is the steering and the eversion, rowing. We call them in technical terms degrees of freedom. Let's call them directions. So I split those 2 directions and I gave only one of them to the human operator. So for example, in this paradigm, I have the human that controls only steering, and the eversion is actually controlled by the robot, is automated. So all the robot does that. And then the other one has the other way around. So the human operator only controls the eversion, tells the robot when and how much to evert. while the steering is done automatically by the robot, because again, the robot knows where to go. And then in the end, the very last one, I implemented a mostly autonomy scenario, which everything is automated except for the gripper, which is controlled by the human operator. So actually only the release of the gripper, because the grasping is, since it's based on magnet, it's kind of automatically done by the robot. And the reason why I did not consider a full autonomous system is because, you know, I wanted to keep the human in the loop. That was the most important thing. Because if you, this is just an easy example, but if you think about more advanced scenarios, the human presence can be a strict requirement. For example, think about surgical robots or rehabilitation, assistive rehabilitation, in which you have a patient that you know, cannot move their arm, and the robot pushes the arm. So if there is no patient, there's no task for the robot. So we need to have the human in the loop. So if we define, let's say, a shared control spectrum, so all the possible possibilities, that sounds bad, all the possible outcomes, let's say, of control, of shared control, in which we have teleoperation, full teleoperation on one side and a fully autonomous system on the other side, we can place the paradigms that I just showed you in this fashion, moving towards automation. So we have a fully teleoperation system, which is outside the spectrum because that's not shared control. And then we have a little bit of assistance, a lot more of assistance. Actually, there's always assistance there. And then we have a complete autonomous direction of the robot, degrees of freedom. And then in the end, we have a mostly, almost everything is autonomous. So again, enough with words. I have a video. This is a video of the execution in full teleoperation. And in fact, as you can see, the hand that interacts with the robot actually moves, and the robot replicates the same movements of the hand. Yeah, I just want to show you that. Also, the gripper is controlled by human. Everything is controlled by the human. And then in the next video, I have the mostly autonomy paradigm. In fact, you might notice that the robot is moving by itself without the operator sending any command. I try to be still here so you can actually see what's going on, except for the gripper. If you can look carefully, you will see that the hand of the operator is actually pushing a button on the interface, which releases the item. And I will not show you the other paradigms because without feeling, for example, the haptic feedback, you wouldn't appreciate the assistance. So that kind of deceives the purpose. Okay. So as usual, as a researcher, I ran a small set of demonstrations with a small number of participants because we were on pandemic here. And without spending too much words on every single outcome that I have, I just want to point your attention to what I believe is an interesting finding. So all the results that I gathered, they all present this type of trend. As the autonomy increases, the robot was able to place the item with decreasing error, which means better performance, which also means that sharing the control between human and robot, and actually soft robot in this case, actually does improve the performance. But what this data didn't tell me is that the feeling of interaction decreased with autonomy because the human was less involved. So yes, it's so cool to see a robot performing the task, but if you want to be in the loop, you also need to have control over it. And it's important because sometimes also the robots can do mistakes. Also humans can do mistakes. So it's kind of like of a trade-off. I will publish this tomorrow. I will submit this journal, this publication tomorrow on a journal. So let's keep my fingers crossed and let's hope for the best. All right. So the last topic that I wanted to talk about is, as I already said, not much related to interaction, but I think it's a very fascinating example on how we can use artificial intelligence to build and design our personalized soft robot. So a very interesting thing of soft robots is that we can have them in different shape. This is the robot that I showed you so far, which kind of only grows and moves as a rigid body. But then there are different other ways, the different robots like these ones or this one that I already showed you earlier. So bending and steering, so how the robot moves in the environment, can be cable driven. So there are motors and cables that can just pull the body of the robot. Then can be performed by tendons, or for example, like in this case, they can also not be actuated at all and leave the robot to deform itself, its body, thanks to the environment. And when I say actuated, I mean motorized. So for some soft robots like this one, actually, we can model them as a set of links and joints. So wherever we bend, there is a joint, like the little dots. And the body of the robot can be composed of links. So these segments. So the type of soft robots that I'm currently working on, so they are different from the cases that I showed you earlier. What I'm currently working on, those type of robots can be actuated and perform bending at certain locations. So we're talking about robots that you can command them to bend at specific points. So actually we'll show you what I'm talking about. So we have our soft robot container, right? And then pressurized air makes it grow, forming a segment. And then we reach a point in which we place the joint. And we can actually bend the robot, let's say, of this angle. So we keep going until the robot is fully grown. So the design of a soft robot, of this soft robot, and I'm using a technical term, design, the design in this case is defined as a set of links with different lengths, like in geometry. So link, link, link with different lengths, right? And this is not too much different from any other robot, if you know a little bit of robotics and kinematics. But the very specific part of this robot is that they can grow. So remember, they can grow, they can invert. This means that the end of the robot, the tip, like this is the tip, this is the tip, the end. This one is the end. We call it end effector, but let's call it tip for today. So the tip of the robot can be placed anywhere in this segment because they can grow, right? So imagine the robot goes and it stops growing here. So you have a wide range of points where the end of the robot can be. And that's, the difference between this kind of robots and the industrial robots that you see every day, let's say. So during fabrication, when you go in the lab and you want to build your own soft robot, you can place these joints following the design. So you want to make a segment of 1 meter, for example, and then you put a joint. Then you make another segment of 0.5 meter, and then you put a joint, and so on. I will not discuss how we make joints because I'm not a mechanical engineer, I'm a software engineer. So I will talk about how do we get this design. Well, that's actually one of my research objectives, which is to create a tool to optimize the design, to get the best design. To get a best design of a soft robot to reach a given set of targets with a given orientation in an environment, let's say with obstacles, right? So what we need is to find the length of all the links such that the robot can, such that you can fabricate the perfect robot for this specific task. So for example, something like this, where the robot reaches all the targets with a single design. This is the same robot. There are 3 different configurations to reach those targets, but this is the same robot. And in fact, all these 3 configurations share the same design because the lengths of all these links are the same. You can check that they are really all the same. Of course, except the last one, because again, remember, the robot can grow. So that's the very, very interesting part of soft robots. So how do we get this design? Well, we need an optimization tool. That's how we call it, optimization tools. And my favorite one is genetic algorithms. And if you're not familiar with genetic algorithms, well, they are a specific search algorithms, which is part of artificial intelligence, by the way. specific search algorithms based on Darwin's evolutionary theory, in which solutions of a problem are codified as individuals. Pairs of individuals are combined together such that the respective offspring inherit their features, and eventually they evolve towards better solutions. And I know that you didn't understand a thing I just said because I was too fast. So let's see an example of what I meant. So let's understand what this optimization method genetic algorithm is, because it's very interesting. So very quickly, when we want to optimize a certain something, let's say a function like this one. So we have the formula of this function. We cannot see it. Imagine we cannot see it. So what we are doing during optimization, well, we're simply searching for either the maximum or the minimum of this function. And we use the word optimizing because this is the best value that we can get out of our function. Or of course, the worst, which is the opposite of the best. So the procedure is simply inverted. So we can solve this optimization problem analytically if we know the formula of the function, which we do, by solving complicated math equations, lots of formulas, variables, gradients, calculus. It gets even more complicated when you add more dimensions, more variables, and almost nobody likes that. So the idea is to randomly search for values of our function and evaluate how good or bad they are with respect to our optimal solution. So these are just random numbers. I generated random X values, and then I got their solution. And then I check how bad or good they are based on what I'm looking for. Let's say the minimum. So as I mentioned before, how do we get the minimum? As I mentioned before, Darwin's natural selection theory gave these two gentlemen that I have here in my reference, Goldberg and Holland. So the absurd idea of using evolution to find minimum and maximum of a function. And if you think about it, in nature, species adapt to their habitat, they evolve from their predecessor, and they become stronger and stronger as the time goes by. But unfortunately, weak individuals that can adapt, they eventually die. That's just nature's law. At least it was like that before the humans, came into the picture, but that's another story. So, well, that's in a nutshell how a genetic algorithm works. So let's say that we want to find a minimum of this function. And this is our optimal solution, which we, of course, don't see. We don't know. Otherwise, what's the point? You cannot see the graphical representation of the function. We only have the formula. So a genetic algorithm would generate random solutions, for example, these two. And these solutions are then combined together. For example, if they are numbers, we can get their average, but there are other ways. This operation is called crossover. The combination of these two solutions generates a child, exactly like in natural reproduction. So as you can see, this child is closer to our optimal solution than its parents because its value is smaller than its parents' values. So this solution will be preserved and it will be used in the next generation in order to generate even better solutions. And of course, it can also go the other way. So two solutions generate a child which performs worse than its parents or one of its parents. This child will be discarded because we already have a better solution. Or actually, we would discard the bad parent because we want only the best to survive. However, something bad might still happen. And for example, this solution here, it's in a local minimum. And if we keep, iterating this and make those two reproduct, those solutions reproduct, we will always be stuck in that minimum. Of course, we don't know where our optimal solution is. So what we know is that might actually be the best solution. In fact, in this example, it's easy to see that that's not, the best solution. But if you look at this one, for example, what is the minimum of this one? So we have no idea, and good luck finding it without optimization methods. So to prevent being stuck in a local minimum, genetic algorithms use mutation, just like our DNA, which is a good thing and a bad thing, depends on what happens. So the newly generated solution, this child, is mutated to something else. We can just change the number randomly. And as you can see, this solution is smaller than the previous one. So we got lucky and we escaped the minimum. But of course, the local minimum actually. But of course, this can also be bad. It can also have gone worse too. So this operator must be used with caution. So if you keep iterating this procedure with crossover and mutation, eventually you will find a solution which is very, very close to the optimal one. And this works. And that's why I like this method so much. So going back to the soft robot problems, because there was like a big introduction on optimization. So let's see how I can apply these genetic algorithms to generate the best design for our task that we can actually follow to build the perfect soft robot for this very task. So suppose we start from this container from the home. And then we want the robot to reach the start, our target, with this specific orientation. And let's also suppose that we only have 6 segments. We want to build a 6-segment robot, maybe because this is what we can afford in terms of time and cost. That's not really important right now. That's a constraint that we have. So we want to solve this problem with only 6 segments. So the genetic algorithm will generate 6 random lengths for each segment, right? Everything is random. And based on these lengths, it will generate random solutions. So a solution is a single configuration, like this one, for example. And with random solutions, we might have different configurations. Everything is random here. So how does the genetic algorithm decide which one is the best? Well, we can calculate the distance between the tip of the robot and the orientation segment, right? So our objective would be to minimize this distance. So the bad configurations will not survive this generation. They don't have the minimum distance, so they will be discarded. But it's not over because we only reach the orientation target, the orientation segment. We need to add a further segment to reach the target. So what we would do is to also minimize the angles between the last segment and the orientation line. And this is useful such that we don't have a robot that curves abruptly. Like in this case, we would have a 90-degree angle. That's not what we want to do. So this one turns out to be the one with the minimum angle. And so if we add a further segment to reach the target, then you have it. This is the best solution. So imagine that this algorithm iterates on several generations and your solution will get better and better every time. Yeah, of course, there's much more into it. What I want to do is to minimize a lot of things altogether, a lot of matrices, or actually maximize, let's say, the distance between the obstacles such that, you don't go inside an obstacle. But I just wanted to give you, a little introduction on what I am doing right now and how we can apply this artificial intelligence search algorithm to build soft robots. These are some results that I obtained with my optimizer. In this example, there are 4 targets and there are no obstacles, and the same robot actually is reaching them perfectly. In this second one, we have 2 obstacles and some sort of two targets and some sort of wall of obstacles, like a box. The robot comes from here and reaches the obstacles. And the one on the right, this one, is a case in 3D, so it might be hard to see it properly, but the robot is actually avoiding that column and it's going for the targets. So again, I hope that with this brief example, I gave you a clear glance on how we can use optimization tool to a real problem to build, in our case, a soft robot, an efficient soft robot. So yeah, with this, I conclude my presentation, and thank you very much for listening. And I would be really happy to answer your question if you have any. Thank you.
Thank you so much, Fabio, for this presentation. Nihat Hocam, please.
Fabio, thank you very much. Very instructive, and you're so involved with your work, and there's so many aspects to it. It is really inspiring. Thank you very much.
Thank you.
I have a question, which I think is I think, maybe I'm wrong, is a basic difference between humans and robots. Robots are so perfectly built. However, as a human being, I carry inside of my brain many contradictions. Inside of my personality, I carry many contradictions. Too much of it is bad, of course, but I have we all have it. It doesn't fit perfectly. Even in the brain, I mean, I do a little bit of spin glasses, brain science. There, all the neurons are not perfectly smooth with each other. There's frustration loops. This is getting too technical. In society, we have different human beings, which contradictions. We don't always get along, and that, in fact, that's something positive. We have groups of human beings, countries that don't get along. When it gets too much, of course, as soon as it's bad. But I think this is an important piece of evolution. If everybody fit together well, if everybody complied with each other, we'd be just like bees or ants. We would not have to change, or sharks in the sea. So this contradiction really, is, for some periods, it is harmful, but then something better comes out. So I spoke too much, but do you have any ideas on this to build robots which have personality contradictions, which may, have a personality crisis, etc.?
Well, I actually don't think that we are, take my first of all, that's a great observation. So don't take my answer as like, too much seriously. I don't think that we are too much different because, as you said, we think about a lot of things. So we make mistake, but I can guarantee you that robots are not perfect at all. So they also make mistake. And that might be like kind of a contradiction. Like, for example, if we have a robot which is smart, and the way you actually build smart robots is through observation. So you give them a certain set of observation, and you say, this is bad, this is bad, this is good, this is good, this is bad, this is good. So the robot learns on them. But then when it comes to decide on something that the robot doesn't know, that has never seen before, then the robot is like conflicted. You say, okay, is this, I don't know this before. I've never seen this. Is this good or this is bad? And it depends actually on the experience, just like humans, right? It depends on the experience. It depends how many cases the robot has seen before that is pretty similar to what is facing right now. So if you want to see it in a philosophical way, yeah, that's like robot's contradiction. Robot doesn't know. He has to learn from what it, his knowledge base. And I don't think it's too much different from humans. I mean, if you were to find yourself in a situation you have never been so far, you would draw from your experience, and then you would just hope for the best. So you say, okay, more or less, this is what I have in mind. So let's see what happens. And that's kind of like the same that happens with robots. This is like a very, very short description of machine learning, which I didn't discuss right now here. But another interesting thing that you were saying is like that we should get all together to solve problems. Well, actually, when I was there at Stanford, and I don't know if you noticed that I didn't say, but one of the projects was funded by Toyota Research Institute. And I went there for like a couple of times to see what they were doing. And they had like this robots that were like communicating to each other on how to solve a specific problem. Like, for example, one robot was instructed to solve a problem, and then that robot was saying to another robot, okay, this is how you solve this problem. So if you encounter this problem, then this is how you solve it. So that's like kind of get all together and, solve the problem together. So it would be more or less what you were discussing, even though, humans and robots are very different to each other.
Okay, thank you. Maybe there are more questions, Üyesi Madam?
Yes, any questions or comments that you would like to share? You can raise your hands, you can turn on your mic if you'd like to contribute. Participants, I'm also checking the YouTube. There is a question from YouTube actually, from Tunay Kola Açık. He's thanking you for the presentation. In genetical algorithms, it can take some time for the correct generation for each use. Can there be a more standardized system to design a soft robot? Genetic algorithms that he's referring to.
Yeah, that's a good question. Actually, it's a good observation. So it takes time for a genetic algorithm to find a solution. And that's why, this is not a real-time problem that we're trying to solve. You just think about a task, you know the task you want to solve, and then you just run your software. And it might take 1 minute, it might take 10 minutes. And then after that, 10 minutes maybe is too much. But after that, you get your robot, and then you go in the lab and you build it. But, there are other, so this very research project started with something else. I just want to use genetic algorithms because I like them so much. But another another researcher in my team was using like gradient descent to solve this problem. And that was working as well, even though I think the genetic algorithms were faster. But again, the point is that we are not trying to do this in real time. If we were to do this in real time, I'm not sure what that would be the process, because this is a very hard problem to solve. Maybe quantum computing, I don't know. Maybe that might be a solution, but I don't know too much about that. So I don't know the answer.
Thank you. Thank you so much. Do we have any other questions or comments regarding the presentation, or any other questions regarding human-machine interaction? I was actually wondering, this is the first presentation I've heard about soft-growing robots, and types of robots that we're used to actually when it comes to mind in popular culture is more, I think, hard robots, and there have been so many advancements with those robots, especially in industry and various sectors. Do you think soft-growing robots have as much promising use in the industrial sectors in the upcoming time?
Well, that's a great question. And this is a very recent topic. So the soft-growing robots are growing themselves. So, researchers are not too much focused on that. So we are a small community. I never heard about soft robots before I went to Stanford. But so it will take some time, of course, like everything. But considering that they, you can fit one of them in a very, very small hole, and maybe you cannot enter in that room because there is a fire or there is anything. So that is a very, very interesting thing, a very interesting feature that they have. And an industrial machine, a mechanical robot cannot do the same. So it cannot fit inside a hole. And that's one example. Or another example that comes into my mind is that once we were invited in Tokyo to have a meeting with the people that were responsible to clear the Fukushima, the nuclear plants, and they were looking for this kind of robots that could bend and could enter in those cluttered environments, and they could grow so they can just basically go anywhere, right? And then identify where the radioactive material was. So they were actually asking, okay, are you selling these robots? But we were just, researchers also, okay, we will go there maybe one day, but we're not ready yet. So I definitely can say that if things keep moving in this direction, maybe yes, maybe one day we will be able to have soft robots. I think that's the target, to have soft robots doing more advanced things. But there is a limit, of course.
Thank you so much. Taner Hocam, please.
Okay, thank you, Fabio. This is an excellent presentation. Thank you so much. As I understand, this is just an optimization problem. And also, I was also interested in the optimization because I am interested in the indoor positioning system. The main problem is the optimization. So in general applications, I also use the genetic algorithms in my optimization problem. But I found that the Big Bang, Big Crunch algorithm is much more successful than genetic algorithms. It's much more, the performance is much better. And also speed is very good. And also maybe we can apply a Big Bang, Big Crunch algorithm to your problem. It's just a contribution for this one. But on the other hand, we consider the transfer learning and the imitation learning. So what do you think about the application, the transfer learning or imitation learning to this kind of problem? So I was wondering about your opinion.
So first of all, thanks for the suggestion. I haven't heard about the Big Bang.
Big Crunch.
So Big Crunch, yeah. So I can look that up, and maybe we can have a discussion after the meeting.
Yeah, I can share the algorithm if you want. Okay.
Thank you so much. About the other problems that you mentioned, do you mind elaborate a little bit more on what they are so I can have an idea?
Yeah, the problem is the transfer learning. So apply this learning process in one system, so you get results. So you can apply this with the algorithm by considering the results. So this is the transfer learning. The other one is the imitation learning. And also a human being can provide a necessary route. And also the robot can follow the instructions, just like the imitation of the positioning. Well, can we apply this kind of algorithm?
I don't know actually how to apply that with genetic algorithms or optimization in general, because it feels more like a sort of supervised or unsupervised learning technique rather than, finding a minimum or a maximum. Mm-hmm. But on the other hand, you can actually apply this kind of optimization to find the transfer functions of machine learning systems. So maybe we can join that together. And
okay.
Definitely, I mean, there is more than one application in which you could use genetic algorithms.
Okay, I also share the Big Bang, Big Crunch algorithm with you, so you can apply this algorithm. Thank you so much for the presentation. Excellent, so much. Thank you so much.
Thank you so much for both the question and the answer. Nihat Hocam, please. Your mic is off. Can you turn on your mic? Nihat Hocam, can you turn on your mic?
I have done that, okay.
Yes.
So my question is, do you have robots, designing robots without human intervention? The robots decide to solve a problem and they say, we're going to design another robot, a different one.
Okay,
you laugh, but
that's interesting. That's interesting. I actually don't want to go there, because then we will end up like in the movies where the robots takes over, and then what are you going to do?
No, the robots are taking our jobs.
So then robots will take our job. We don't want to do that. We want to still be here.
We can all do physics. Okay.
But actually once I had to write a software to solve a certain problem. It's not related to robots. And since it was too long, I decided to write a software that will write the software for me. So I don't know if that answers your question. Maybe
you have software designing software.
More or less.
Thank you so much. Do we have any more questions or comments from our participants? So there are things coming from the YouTube chat box as well for the presentation. It was very interesting and inspiring. Thank you so much again, Fabio, for this wonderful presentation. Nihat Hocam, would you like to have the last words?
Well, again, both the presentation and the discussion afterwards was very interesting. And I hope we have more of it among ourselves, among the people from outside our university. So Fabio, I thank you very much for this very nice and instructive occasion. Thank you very much.
Thank you for having me.
Okay, so we've come to the end of another online public colloquium of Kadir Has University. This time we'll be meeting next week, actually, on the 9th. So I would like to note that down for your calendars and hope to continue to see in our other colloquiums in the future. Thanks so much for joining us. See you next